You will learn about the abstract data type priority queue and the data structure heap. We start out with an application of priority queues and heaps. In particular, we look at simulation. Then we introduce the abstract data type priority queue, which is used in event-driven discrete simulation. Priority queues can be implemented effectively by the heap data structure. Finally, we see another use of heaps, which is a sorting technique called heap sort. So let's start out with the application. Simulation is a model of the real world where you abstract the real world to some features you are interested in. For example, a street map is a model of the real world that only displays the street system. However, simulation is even more than that. A simulation displays the changes over time, so it is a dynamic model of the world. For example, a simulation may display how the air flows around an airplane, so engineers can decide on the best shape of an airplane. Now in this example, the changes over time are continuous. We look here only at discrete simulation, where changes occur in discrete intervals. These intervals might be discrete time intervals. Say the model displays the changes that occur in the real world every hour. Or the changes might be caused by discrete events. Simulation is frequently used to make predictions or to experiment with different scenarios without having to change the real world. So simulation is typically a much cheaper way to experiment with different options. For example, the police might want to decide if the addition of a traffic light will improve a bottleneck at an intersection. In that case, data will be gathered beforehand. For example, about the number of cars going in each direction at different times of the day. Then the simulation displays different possible scenarios of traffic light settings. The specific simulation application we look at is a waiting line simulation. Monitoring a waiting line fits many situations where event-driven discrete simulation is applied. For example, a bank might want to determine how many tellers are required to keep the waiting time in the line low. Similarly, a call center might want to reduce the waiting time, or the waiting line might refer to the waiting cars at a traffic light, and so on. In each of those scenarios, we have the clients that are waiting in line. So a client might be a bank customer, or a car, for example. Then there are operators that handle the clients waiting in the line. An operator might be a bank teller or a traffic light. Let's be more specific and look at how to simulate the waiting line at a bank. Note that we're only interested in monitoring how long the waiting line is. The events that change the length of the line are A. the arrival of customers, and B. when a customer leaves the line because a teller is available to serve a new customer. Before starting the simulation, some data has to be gathered. In particular, we need to determine the arrival rate of customers and the service time per customer. When running the simulation, we need to determine how many tellers should be used. The basic framework of the simulation is very simple. The simulator keeps generating the events that are happening, and while there is an event that has not yet been processed, we get such an unprocessed event, process it, and possibly add additional events that arise when processing the event. We will consider which kind of collection we need for this simulation framework, what are the operations on these collections, and then later how to implement these collections. For the waiting line simulation, like the bank simulation, we will need a collection for the customer standing in line. We can use a queue, as a queue works exactly like a waiting line. The second collection is needed to track the events that have not yet been processed. We only need to be able to add new events to that collection and to remove these events. However, events should be removed in chronological order here. So we could assign a timestamp to each event and then always removing the event with the lowest time value. That is exactly how a priority queue works. We can add elements in a priority queue, each with its priority, and remove the one with highest priority. In case of the simulation, the priorities correspond to the timestamp, where the lowest timestamp value has the highest priority.